In this final section of the course, we'll go through some interesting concepts that are usually considered a bit more advanced. However, you're guaranteed to stumble across them while working with React and the surrounding ecosystem. One of the most common things that's difficult for newcomers to grasp, yet is often expected of them, is the knowledge of some functional programming patterns. Now, functional programming is a paradigm, a way of building software, and you already started using it in this course. Remember how we explained that React is declarative? That's one of the hallmarks of functional programming. Or remember when we talked about pure functions, referential transparency, and the trouble of having side effects? Those are all major functional programming concepts. Feel free to pause this video and review those concepts if you want. As for this video, we're looking at a functional programming approach to dealing with collections, specifically the famous trio called map, filter, and reduce. So if you look at my index.js file, you'll notice that I've once again added some playground component instead of a regular app component. If we jump into this component, we can see that it's a simple class that renders some component called rating card. And this rating card is a component that simply takes in a number and prints out some stars. Let's test it out with a couple of different values just to confirm that this works. Now I'm going to introduce an array of objects that look like this. And as you might be able to guess, our goal here is to take this array, calculate an average, and then print that as the number of stars. However, not every score is valid here. If flagged is set to true, we want to skip the rating. If an object is empty, like this one, we obviously want to skip it. And if the user ID is undefined, we want to skip that as well. You can think of this as a filter that only allows ratings from authenticated users who are not flagged as spammers. So I'm going to reach into my git stash and show you a function that does this. And before we discuss it, let's just plug it into our component. Also note that since this function will return a floating point number, we're going to round it, because our component accepts only whole numbers. And now if I decrease this number here, we'll see that the average rating will go down. Now as for this function, there's a lot going on for a simple piece of code. But to make it more fair and easier to read, we'll extract this if condition into a separate function. Okay, great. We can analyze this now. What we're looking at is a function that's written in an imperative paradigm. I'm going to try and explain why this code is more complex than it meets the eye, and why I try to avoid ever writing something like this in my own work. First off, we declare some sort of local state that we'll be forced to manage. I generally don't like this. Setting a counter to 0 at the beginning of a function is a leftover habit that many of us have learned at college. And this usually comes when programming with C. Now, in a high-level language like JavaScript, we have tools that help us avoid this pattern completely. Next, we're doing some iteration over the entire array, and notice how many of these names don't make much sense. For the given domain, it's hard to find many that are appropriate. We're mixing scores and votes here. We also end up with score.score at some point. This imperative approach has led us to write code that requires that we invent a bunch of new names. And as you know, naming things well is a hard task. Next, we're doing some sort of filtering, and then we have some incremental logic. And then finally we have some calculation at the end. Now let's look at this same functionality, but rewritten using filter, map, and reduce. Right off the bat, some of the syntax here might be confusing. This is likely because we're using the underscore as a variable name in all three functions. Why? Well, this is actually a common pattern when writing functional code. Consider this. We're calling filter on an array that's already called scores. Of course, the element is a score item. We don't have to bother writing the name of that element because we ultimately don't care about it. Writing the underscore helps us focus on the rest of the logic and saves us from the strain of coming up with a better name. I'm going to replace the logic inside of the filter function with the other function that we created previously. Now we could write it like this, but the filter method already accepts a function that it will call with the element item. So this is actually redundant. We can just write it down like this. Okay, so this should be clear now. The filter and the map help us filter out the bad scores, and then we remap the array to a simple array of numbers. Once we're done filtering, we only care about the numbers. So what does this reduce function do? Well, let's look at the signature of this method. Reduce accepts two arguments. One is a function and the other one is an initial value. In our case, 0 is that initial value, and this is the function. So what does this function do? Well, it increases the value of some accumulator by adding in the next element in the array. The accumulator starts at 0, which is our initial value. So to test things out, let's plug this in. And now let's observe this simple idea. Assume that we have an add function. It just adds two numbers, right? So that means that we can add it in here, right? But doesn't this whole thing look redundant now? Just like with the filter method, the reduce method just takes in a function and calls it with the parameters. So this entire thing here is redundant. We can just call it with add2 as the first argument. And that's it. And then we just take the sum of all numbers in the scores array and divide it by the length of the array, which returns the average. To test all of this out and make it a bit more clear if you're struggling to understand reduce, let's change some of the data over here. And let's add two console logs. So here's the array of all of our numbers, and then a bunch of logs that come from the add2 function that's being called by reduce. The number on the left is the accumulator, and as you can see, it starts at 0. The number on the right is the next element from our array. You can see from iteration to iteration, the accumulator becomes the sum of the previous accumulator and the last number. Finally, 15 plus 2 will be 17, which when divided by 6 is 2.83. Rounding up, this is equal to the 3 stars that we see on the screen. Now the way we added the add2 function and the isObjectValid function to filter and reduce is another great concept of functional programming. It's called function composition. It's the idea that the result of one function is the input of another one. And just before we close this video off, I'm going to tease you with another interesting concept from functional programming. This is a higher order function. As you can see, it doesn't return a straight result. Rather, it returns another function. So why did we choose to write it like this? We could simply have one function that accepts two parameters. Well, this is a technique called currying, and it allows us to have a reusable software component. By providing the tags up front, we've now created a function that we can call whenever we want, and the tags is already applied. Imagine if you're working with different values for the tags. You'd have to constantly juggle which tags parameter to pass. This way you create all the variations that you need and just call the one you want.